In this session we are going to discuss about sampling distributions and point estimation. Already we discussed in the previous lecture, we discussed about the sampling methods. Now see the objectives. In this session we are going to introduce the concept of sampling distributions. Under the sampling distributions we discussed two things: the sampling distributions of sample mean and the sampling distribution of sample proportion. And the end of the this lesson we are going to define the concepts of parameter, statistics and point estimator, and just discuss about the properties of a good point estimator. That means we just start the inferential statistics estimation. Under the estimation chapter we just discuss about the point estimation, because there are two estimation methods, point estimation and interval estimation, but in this lesson we are going to just introduce the point estimation. The outcomes at the end of the chapter, students we should be able to identify and apply the sampling distributions of sample mean and sample proportion to find probabilities under given condition, and also you should have a clear idea about the concepts of parameter, statistics, estimator and estimate. Now before move to the sampling distributions, you should have an idea about what is mean by parameter and the statistics. Already, as we mentioned, the parameters means the characteristic of a population. That's why he has indicate that characteristic of a probability distribution, because we use the probability distributions to explain the characteristic of a population. For example, characteristic of probability distributions: mean mu. Now this is the mean mu of the population, population proportion. The sigma square indicate the variance. To make a decision about the population characteristics, we usually use the statistics. That means the summary value calculate from a sample. Sample characteristic we call as a statistics. For the mu, the relevant statistic is x bar. To present the population parameter, population proportion, capital P, we use simple P, sample proportion. S square is the sample variance, that is we use to make a decision about the population parameter variance, sigma square. Then see the general definition for the sampling distribution of a statistics. I think now you have idea about what's mean by statistics. Sample characteristic. The sampling distribution of a statistic is the probability distribution of all possible values that can be assumed by a statistics when computed from random sample of the same size. Therefore, the sampling distribution of statistics means the values which are assigned for the statistics can be assumed by a statistic when computed from a random samples taken from the population with the same size. Under this one, we are going to discuss about the two things: sampling distribution of the sample mean and the sampling distribution of the sample proportion. Now see the sampling distribution of the sample mean. How do you define the sampling distribution of the sample mean? Here just see, if can calculate sample means, that means we can, when in the inferential we take samples and we study on the sample observations and calculate the statistic values. Based on these values we try to make inferences about the population characteristics, but there are large number of samples of same size can be obtained from the population. That's why here we indicate if can calculate sample means from all possible random samples. As indicate, there are several samples can be obtained from the population with same size. If can calculate sample means from all possible random samples of size n from a population. These sample means will vary. That means we can calculate the several sample means obtained from the population. These sample means will vary and form a new population. That means there are several numbers we can assign for the sample means. Those values generate or set a new population, which is called the sampling distribution of the sample mean. If the mean, now see how some characteristics or properties of the sampling distribution of the sample means. If the mean and the variance of the population are given, mu and sigma square. Now suppose if the mean and the variance of the population, mean mu and the variance sigma square, that means the variance sigma square means the standard deviation of the population is sigma. Then the mean value of the sample mean or expected value of the sample mean is equal to population mean mu. Now here the theory indicates that the mean value of the sample mean, that means we can obtain the several samples from the population, then we can calculate the separate mean values for each samples, and here indicate that mean value of those sample means, that means expected value of x bar or x double bar should be equal mu. So here mu indicate the population mean. The standard deviation of the sample mean, the standard deviation of the sample means values is equal, we give the also new name for indicate the standard deviation of the sample mean. We call it as a standard error. Standard error is equal, you have to just divide the population standard deviation by square root of simple n indicate the sample size. By dividing the population standard deviation by square root n, we can obtain the standard deviation of the sample means. Now just see one example to clearly understand the concept explained under this sampling distribution of sample mean. Now see this example. Here we have the marks for the 25 students. The first row indicates the student number. Now here see there are 25 students. The second row indicates the individual marks obtained by those 25 students. Now when we go back to here, they indicate that the mean value of the sample means is just equal population mean mu. Therefore see the population mean mu. Here we just add all these marks values, 56 plus 80 plus 54 up to 67, that the total marks obtained by 25 students equal 1607. The total number of students here 25. Then when we divide the total marks by number of observation or population size 25, the population mean equal 64.28. Now suppose we are going to take 10 samples from each size of 5. Size of the sample is 5. That means using a sampling method, here just see using the simple random sampling methods. Now suppose we obtain 10 samples of size 5. When we say if we can calculate, that means suppose we are going to take samples of size 5, all possible samples without replacement is 25 C5. It's gives the 53,750 like samples, but here we just take 10 samples of size 5. Now we are going to calculate the sample means of these 10 samples. That means we are going to see is the given properties is what we discussed in the previous slides is indicate these are correct or wrong using this sample. Now we take 10 samples. Now we are going to calculate the distributions values for the sample mean. Therefore we need to calculate the mean value for each sample. Now see how do you calculate the mean for the first sample as indicate here. Just add these 5 numbers, then divide it by 5. The sample mean of the first sample is 75. Likewise you can calculate the mean value of these 10 samples. Now these values we call as a sampling distribution. That means these are the values that can be assumed for the sample statistic x bar, right? 75, 63.2, 72.2, 61.2, 67.6 likewise. These things we call as a sampling distributions. Now see the mean of the sample means. Now we are going to see the mean value of the sample means, right? Then just add these 10 sample mean values. Here sample mean of the first sample 75, sample mean of the second sample 63.2, mean value of the third sample 72.2. likewise just add these 10 sample means, then divide it by 10 because we have 10 samples. Then the answer equals 64.76. Now here see expected value of this sample means equals 64.76. Now that is very close to the population mean mu 64.28. That is mentioned in the first statement. The mean value of the sample means equal to the population mean mu. In the same way we can also prove the second property. The standard deviation of the sample mean is equal, just divide the population standard deviation by the square root n. N simple n indicate the sample size. I think now you have this idea about the sample distributions. That means when you go back to this one, the sampling distribution of the sample mean is we can calculate the several, we can obtain the several samples of same size from the population, here size n. Then we can calculate the means for the all samples we obtain from the population. Those values will form a new population. That's population we call sampling distribution of the sample mean. And sample distribution of the sample means has these properties. The expected value of the sample mean is equal to the population mean, and the standard deviation or standard error of the sample mean is equal to this one, sigma over square root n. Sigma indicates the standard deviation of the population. Now see there are several cases for the sampling distribution of the sample mean. Now see the first one. Now suppose we obtain the samples from the normally distributed population. Now see sampling distribution of the sample mean. We take several samples and we are going to discuss about the distribution of these sample mean values, and the condition here is given that we take a sample from normally distributed population, and if population variance is known, suppose the population variance is given, we know known value, and see the condition here says that x indicate the individual measures and x follows normal with mean mu and variance sigma square. Then the distribution of the sample mean is also normal for any sample size n. Not need to worry about the sample size because we obtain the sample from the normally distributed population. Then the theory says that the mean distribution of the sample mean x bar follows also normal with the population mean mu and variance sigma square over n. That means we have to just divide the population variance by sample size n. Right, here just indicate the next formula to how we convert this one into standard normal distribution. This is the transformation formula, x bar minus mu over divided by the standard error of the x bar sigma over square root n. Now see the first example that is given in the page number 63. Let's read this one. A soft drink vending machine is set so that the amount of drink dispensed is a random variable which follows a normal distribution. Given that here our random variable is amount of drink dispensed from a vending machine. Those values follows a normal distribution, mean value 200 milliliters and the standard deviation of 5 milliliters. Then ask about what is the probability that the average amount, mean value amount dispensed in a random sample of size 12 is at least 204 milliliters. Once you have this type of question, just first as a first step just define what is the random variable. Now see the answer for this example 9.7. First define the random variable. Let x be the amount of drink dispensed by the vending machine. Then just note down the given information. Here says that these measures or amount of drink dispensed by the vending machine follows a normal distribution with a mean of 200 milliliters and standard deviation of 5 milliliters. Here you can just write down the given information as this: mu equal 200, standard deviation of the population 5. That means we know we take a sample from the normally distributed population and variance or standard deviation is given, known value. Then ask about, just you can write x follows normal, mean 200, variance 5 to the power 225. Then here question, again see the question, what is the probability that the average amount dispensed in a random sample of size 12? Ask about the average amount, mean amount at least 200 milliliters. That means average value is greater than or equal to 100. Probability of this value, the probability of average value is at least means greater than or equal to 104 milliliters. In given conditions, we take a sample from normally distributed population and population variance is known. Then we know, according to the theory, if x follows normal with mean 200 and mean is given and variance known, then for any sample size, the distribution of the sample mean is also normal. Under these conditions, we know the distribution of the sample means is also normal for any sample size. You just indicate the sample size is 12. Not need to worry about this sample size because we have this condition. Then we can say that x bar, mean value of these samples, follows also normal with the same mean of the population 200. Only difference is the variance. To get the variance, we have to divide the population variance by the sample size. Therefore, we know x bar follows normal with mean 200. Variance is equal 5 to the power 2 over 12. Then see the question. Just convert the question into the probability statement using x bar. Then here asks probability of this mean value is at least means greater than or equal to 104. Now we need to find this value, and we know x bar follows normal with mean 200, variance is equal this one. Now first we need to convert, to get the probability values, we need to convert x bar values into standard normal. Here given that x indicate amount of drink dispensed by the vending machine, x bar indicate the mean value of this amount dispensed by the vending machine. X follows normal. Under the given condition, we know x bar follows also normal, mean 200, variance this value. Then using this transformation, x bar minus mu over standard error or standard deviation of x bar. Then see how do you get the standard deviation of x bar. Also we know the variance, just take the square root of this one, or using the theory just divide the population standard deviation by the square root of sample size, or just take the square root value of this one. That is equal 5 over square root 12, that is equal 1.443. Then using, now we all these values is known, variance of x bar is also, standard deviation of x bar is also known, 1.443. Then using this transformation equation formula, we can convert these values into standard normal values. And use this transformation, x bar minus 200 because mean equal to 200 divided by standard deviation of the x bar 1.443. Then you can convert this 204 into corresponding or relevant z value. Then finally you need to find the probability of z is greater than or equal to 2.77. Then just draw this, indicate using the standard normal distribution, mean equals 0 for the standard normal z curve. Now this is the required area just given here. Z probability z greater than or equal 2.77. I think we can think 2.77 somewhere here. Then we need to find that probability. This equal just 0.5 minus this total area from 0 up to plus infinity, this area equal 0.5. Then just read 2.77 from the table, standard normal table. That value is equal 0.4972. Therefore answer equal 0.0028. That way you can find the answer, right, for the example 9.7. Now see the second case. Earlier we discussed about sampling from normally distributed population with non-variance. Now the conditions for here, we are going to take a sample from a non-normally distributed population but population variance is known, and the other condition is large sample. Size is greater than or equal 30. For the case where sampling is from non-normally distributed, that means we don't know about the population, where we take a sample. For the case where sampling is from a non-normally distributed population, then according to the one theorem, it is called as the central limit theorem. For the large samples, if you have this condition, then according to the central limit theorem, now central limit theorem says population with mean mu, variance is or standard deviation is known, sample size n, and the sample size should be large. Large means n greater than or equal 30. Then the distribution of sample mean x bar also follows normal with mean mu, variance sigma square over root tables. Earlier we say that if we take a sample from normally distributed population and the variance is known, for any sample size, mean follows this distribution. But when you take a sample from non-normally distributed population and the population variance is known, and the large sample, if condition, the important condition here is that the sample size, if the sample size is greater than or equal 30, then again we can use the same result, x bar follows normal with mean mu, variance sigma square over n. We can prove this one by using the central limit theorem. Then see the next example, 9.8, page number 63. The mean life of a certain saw blade is 41.5 hours with a standard deviation of 2.5 hours. Then ask what is the probability that a simple random sample of 50 saw blade has a mean between 40.5 and 42 hours. Then see the answer, example 9.8. Let x be the lifetime of a certain saw blade. Write down the given information. Here given that mean value of the population 41.5 hours with standard deviation, that means variance is known 2.5 hours. The distribution, this didn't given about the distribution of these measures, therefore we don't know about the distribution of the x. Distribution of the x is unknown. That means we can assume we take a sample from non-normally distributed population. Population variance is known and the sample size is large. Here given that the sample size is equal 50, that value is greater than 30, therefore can be considered as a large sample. Then see the question asks here, what is the probability that a simple random sample of 50 saw blade has a mean? Just ask about the mean value, and we need to write the or identify the distribution of the mean value of the lifetime of a certain saw blades. Then according to the given condition, can apply the central limit theorem, because even we take a sample from non-normally distributed population, standard deviation or population variance is known and the sample size is large. Therefore we can say that according to the central limit theorem, the mean distribution of the mean value of the lifetime of saw blades follows also normal with the population mean 41.5 hours and the variance of x bar 2.5 to the power 2. That means variance, population variance, we need to divide by the sample size 50. Therefore the standard deviation here, variance of the x bar equal 2.5 to the power 2 over 50. This is the probability as a question. What is the probability that x bar mean value lies in between 40.5 and 42? In the population, mean value of the saw blades x, mean value of x defined as the lifetime of the saw blades, mu x equal 41.5. The standard deviation of the lifetime of the saw blades 2.5. Then according to the central limit theorem, we can say mean value of the lifetime of saw blades follows normal with these parameter values 41.5 and 2.5 to the power 2 over 50. When using this transformation, we can first convert the x bar values into standard normal. Standard deviation of the x bar equal 0.3536. Use this formula to calculate the standard deviation of the x bar. Then converting these values, using this process, we can convert the x bar values into z values. X bar, x value minus mu divided by standard deviation of x bar. Then we need to find the probability of standard normal distribution. That means z values lies in between minus 2.83 and 1.41, and just mark the required area. Minus 2.83 somewhere here and 1.41 somewhere here. Then using the standard normal table, we can find the corresponding probabilities. To get the probability from minus 2.83 to 0 according to the symmetrical behavior, just read the z value from the table. Z value equal 2.83 from the table, that is equal 0.4977. Just to find the probability of z values lies in between 0 and 1.41, just read z equal 1.41, that is equal 0.4207. Just adding these two values, we can obtain the final answer, that is equal 0.9184. Now we can move to the next part. Earlier we discussed about sampling distribution of the sample mean under the two cases, sampling from a normally distributed population and sampling from a non-normally distributed population. Now here we can discuss the sampling distribution of the sample proportion. Here particular of interest for qualitative data is the proportion of times as a particular outcome success. Particular outcome can be defined as the success, focus number of successes obtained as a ratio. Now see here this example. Let P be the proportion of girls in the selected sample from a group of students. Our success is the find the proportion of girls in the selected sample. Now suppose here proportion of girls, the population size equal, here just indicate the boys 233, girls 241. To get the proportion of girls in that population, just divide the number of girls in the population 241 divided by the total number of observation in the population. Just add these two, 241 plus 233. The answer equals 0.508. Approximately this equal 0.51. Here state that to estimate the population proportion, the capital P indicate here given in red color, the population proportion P, we use the sample proportion simple P. Capital P represent the population proportion. To represent the sample proportion, we use simple P. The sample size large, for large N, the distribution of P. Here again we just describe the sampling distribution of population proportion. Therefore, for large n, the distribution of sample proportion, simple P, is approximately normal with mean P, capital P, that means the population proportion, and variance can be calculated using this formula. Population proportion into 1 minus population proportion P. They take the product of P into 1 minus P, then divide that value by sample size n. Here says that simple P follows normal with mean P and variance equal P times 1 minus P over n. Here P indicates the population proportion. Therefore, we can write this result as P, simple P. Sample proportion follows normal. Here mean value is equivalent to population proportion. Variance also can be calculated using the population proportion P in terms of P times 1 minus P over n. Now see the next example, 9.9. Again it is given in page number 64. Just read the question. The Finlay Iron Works manufacturer of nails has found that 3% of the nails produced are defective. Therefore, our success is the defective proportion. Here given that population proportion capital P equal 3%, that means 0.03. Here suppose that a random sample of 300 nails is examined. Here sample size is 300. Then ask about the probability that the proportion defective of sample is between 0.02 and 0.035. Let's see the answer. Capital P represents the proportion of defective in the population given that 3%, that means 0.03. Then let simple B be the proportion of defectives in the sample according to the given condition, that means sample size is large. P follows a normal with mean the population proportion 0.03 and variance P times 1 minus P over n, 0.03 into 1 minus 0.03 over 300. Then we can say that P sample proportion follows normal with mean 0.03, that is the variance value 0.1, 2, 3, 4, 4 zeros and 9, 7. Then just write down the probability statement based on the question. What is the probability that the proportion defective of sample is between these two values? And simple P lies in between 0.02 and 0.035. Then again use the similar process. That means first convert these values into standard normal values. Mean value of the sample proportion 0.03. The variance standard deviation equal 0. Just take the square root of the variance, that is equal 0.0098. Then using this formula, transformation formula, just convert these proportion values, P values, into standard normal values. 0.02 minus mean value 0.03, then divide it by standard deviation of the sample proportion. Then finally we need to find the probability of Z values lies in between minus 1.02 and 0.51. Then first indicate the required area, minus 1.02 somewhere here, 0.51. Then using the standard normal table you can read, that means just read 1.02 and 0.51. Z equal 1.02 to get this area from minus 1.02 to 0 To get the probability values from 0 to 0.51, just read z equal 0.51, and this value equal 0.3461. The probability from 0 to 0.51, 0.195, and the answer equals 0.5411. Right. Now see the exercise number 1 given in page number 64. Now just read this one. An airplane is only allowed a gross passenger weight of 8,000 kilograms if the weights of passengers traveling by air between Toronto and Vancouver have a mean of 78 kilograms and a standard deviation of 7 kilograms. Then he finally asks, find the probability that the combined weight of 100 passengers will exceed 8,000 kilograms. The airplane is only allowed a gross passenger weight of 8,000, but here first define the random variable. We can define let x be the weights of passengers traveling by air between two cities, Toronto and Vancouver, but here not given. X follows normal, but standard deviation, population standard deviation is given. Mean value 78 kilogram and standard deviation of 7 kilograms, and the sample size is large, 100 passengers. Then probability combined weights of 100 passengers greater than or equal 8,000. He asks about the probability that the combined weight, the sum weights of 100 passengers greater than or equal 8,000. By dividing both sides by 100, we can convert these given values into mean. The sum of weight of 100 passengers divided by 100 gives the mean weight of 100 passengers. Therefore, mean weight of a passenger, the finally we can convert it as probability of mean weight of a passenger greater than or equal 80. Just divide both sides by 100. Therefore, finally ask about the probability of x bar is greater than or equal 80. Then we need to identify the distribution of x bar. Sample mean. You given that mean value of the individual passengers, weight of the mean weight of the individual passengers 78 kilograms, and the standard deviation of the weight of the passenger 7 kilograms, and the sample size is large. Therefore, according to the central limit theorem, we can say that x bar also follows normal with same mean 78 kilograms, and the variance of x bar is equal, just divide the variance of individual weights by sample size. Therefore, x bar follows the normal with mean equal 78, variance is equal 7 to the power 2 over 100. Once we identify the distribution of x bar, then we can find the corresponding probability. Probability x bar greater than or equal 80. These are the given condition. Mean value of the weight of weight of passengers 78, standard deviation equals 7. Then according to central limit theorem, x bar follows also normal with mean 78, variance is equal this one 49 over 100. Then using this transformation formula, we can convert these x bar values into standard normal. X bar minus mu divided by the standard deviation of x bar 0.7 and divide this difference by 0.7. Then we need to find the probability of standard normal z values greater than or equal 2.86. Then as we done earlier, just draw or mark this required area in the standard normal curve, 2.86 somewhere here. Then we need to find this shaded area. Then just read the 2.86 value from the standard normal table. Then we can obtain the probability values from 0 to 2.86. the right hand side, the probability of the right hand side equal 0.5 minus this value gives the required answer, 0.0021. The second exercise, suppose speed of vehicles on a particular stretch of roadway are normally distributed. It means 36.6 miles per hour mph and standard deviation 1.7 mph means miles per hour. Now see the measurements given here. Suppose speed of vehicles, therefore also here define the speed x can be defined as the speed of vehicles, and also given that the speed of the vehicles are normally distributed. It means 36.6 and standard deviation, that means population variance is known. Here just ask the question, find the probability that the speed defined as x of a randomly selected vehicle is between 35 and 40. Here just ask about the probability of x, that means just the speed of the vehicles. Second part, ask the probability that the mean speed about the x bar. That means we can take a sample from this normally distributed population, then we can calculate the probability of mean value of this mean speed of the vehicles lies it between 35 and 40. Now we can do one by one. First define x speed of vehicles. Given that x follows normal with mean 36.6, the variance 1.7 to the power 2. Now this is the question part 1. He has to find the probability that the speed x lies in between 35 and 40. Then convert the x values into standard normal z values. I think now you know, familiar with this process. Just subtract individual values from its mean, then divide it by standard deviation 1.7. Then these are the corresponding z values, minus 0.94 and 2. Then just mark the required area as shown in this graph. Therefore these two values just directly can be read from the standard normal table. From minus 0.94 up to 0, that probability equals 0.3264. The second probability value from 0 to 2, 0.4772. Just add these two, then the answer equal 0.8036. Then the second part now has to find the probability that the mean speed x bar indicate the mean speed of the vehicle of 20 randomly selected vehicle is between 35 and 40. Initially given that x values, that means we take a sample from normally distributed population, therefore not need to worry about the sample size. X follows normal with these values, therefore we can say that x bar follows also normal. That means we take a sample from normally distributed population and population variance is known. Therefore x bar follows normal with mean 36.6 and the variance is equal this one 1.7 to the power 2 over 20. 20 is the sample size. Then we need to calculate this probability. Mean values lies in between 35 and 40. Again, convert x bar values into standard normal using this process. P probability of z lies in between minus 4.21 and 8.94. That means the required area, almost whole area, that means the lower value is minus 4.21. The 97 point something lies in between minus 3 and plus 3, but here minus value is minus 4.21. the upper value is larger, 8.94. therefore almost this value should be approximately equal to 1. Right, now we complete the sampling distributions. We discuss two sampling distributions. Sampling distribution of sample means. There we discuss two cases. Sampling distribution of sample means when we take a sample from normally distributed population with known variance, and we take a sample from non-normally distributed population. Then we discuss the sampling distribution of population sample proportion for large samples. Right now, then we can move to the second part of this lesson, and also when we are going to move to the statistical inference. Now at the beginning of this lecture series, we say that statistics divide into two: descriptive and inferential. Now we, in the initial lectures, we complete the descriptive part. Then up to this point we discuss the probability part. Now we can start the inferential statistics. Here you can clearly see inferential divide into two: estimation and hypothesis testing. Now we are going to start the estimation. Estimation also divide into two: point estimation and interval estimation. As I mentioned at the beginning of this lesson, in that lesson we just discuss about the point estimation. In the next session we'll discuss about the interval estimation. Now first see the idea about how to define the inferential statistics. The overall idea about the inferential statistics means we need to make inferences about the population parameters. That means I think now you have idea about the parameters. At the beginning of this lecture I explained about what is mean by parameter. Parameter means the population characteristic. To make a decision or infer decision about the population parameters, usually we take a representative part, that is we call as a sample. Then we studied on that sample observation. That means we compute the statistics values. Here statistics indicate the sample characteristics. Based on these statistics values, computed statistics values, we make inferences about the parameter. That process we call as inferential statistics. Now here see, we want to learn about population parameters such as mean, population mean mu, population standard deviation sigma. Then we take a sample, then we calculate the relevant sample statistics. To make inferences about the population mean mu, we just use the statistic x bar, sample statistic relevant sample statistics for mu x bar. The S means the sample standard deviation. Based on these sample statistic values, we can make an infer or decision about the population parameters. Now see the estimation, point estimation, how to define the point estimation. Now we calculate, point estimation is we just calculate the single value for the sample statistic. That single value we use as an estimate of a population parameter. Now here you can see the two words estimator and estimate. The calculation of a single value using a sample statistic to use as an estimate of a population parameter. Interval estimation, in the point estimation we just compute the single value for the sample statistic, but for the interval estimation we just calculate the range of values. That's why we call it as an interval. Determination of an interval of values, the range of values with the population parameter must lie with the given confidence. Here just we calculate the range of values which the population parameter must lie, and also we give the confidence level. Those things will be discussed in detail in the next session. Today in this session we just concern about the point estimation, that means calculating a single value as a estimate for the population parameter. Then just see the difference between estimator and estimate. Estimator is a statistic. Statistics, earlier we defined what's mean by statistic. Statistic is a sample characteristic. It is also can be defined as a function of a sample data. Estimator is a statistic used to estimate an unknown population parameter. Example for the, now these are the first, now see this table. In the first column just indicate the parameters, that means the population characteristic, mu, standard deviation sigma, population proportion capital P. Now see the relevant estimator. For mu we can use mu hat or x bar. X bar, how do you calculate the x bar? We just need to add the measurements of the sample observation, then divide it by number of observation in the sample. Therefore x bar estimator is a function of a sample observations. The relevant estimator for the standard deviation sigma, first we can calculate the sample variance, then we can take a square root of that sample variance, simple S. Therefore estimator for this parameter is S square. After getting the values per square we can take a square root. In population proportion we can use simple P as an estimator, that means sample proportion. The estimate is a computed value. Estimate is the particular value with the estimator taken on a set of data. For example, if we know the sample observation in the sample, then just we can calculate the x bar values. For example, we can say the mean value of that sample 15.7. That value can be considered as a estimate. This is the estimate for this population parameter mu. The estimator is x bar. Using that estimator we can calculate the estimate value. Now this is now see the example for the estimate for the population standard deviation sigma 2.1. Therefore the estimate is the particular value. The sample proportion, when you calculate the sample proportion using the sample data, 0.3 is estimate for the population parameter capital P. Once you get the idea about the estimator and estimate, then we can move to the point estimation. Now see how to define the point estimation. It's a process of estimating a single value for an unknown population parameter. For example, when you need to make a decision about the population parameter mean mu, we use x bar as a statistic. Then the computed value for this x bar is considered as a point estimate. X bar can be defined as the summation of measurements of the individual values divided by number of observation in the sample. Now here when you see these three, you can see statistic is a function of the sample observation. Now this is the formula to calculate the sample variance, but in the population variance we just divide by the number of observation, but for the sample variance we need to divide this squared errors by sample size minus 1. Now here just indicate how to calculate the population sample proportion p hat, the interest values in the population. As I mentioned earlier, if we need to calculate the girls proportion in the sample, just x indicate the number of girls in the population, x divided by the sample size n. Now see this example, how do we calculate the point estimate, get the point estimation. Now here just this example is for the population mean. Suppose that we are interested in estimating the mean mu, that means we need to make a decision about the population parameter mean of a certain population. Now suppose we take a random sample of size 5. These are the 5 sample observation x1 up to x5, be a random sample of size 5 from this population. Now suppose x1 equal 3, x2 the second value equal 5, x3 equal 2, x4 equal 1 and x5 equal 2. Now we suppose the one sample of size 5 taken from this population given in this set. Then see how do you calculate the sample statistic x bar. Just add these 5 values and divide by 5. This is the estimator x bar. This is the estimator for the mean mu. Then using this estimator we can calculate the point estimation. As just add these 5 values, then divide it by 5. 3 plus 5, 8, 10, 11, 13 over 5. This single value we call as a point estimate for the population parameter mean. We use this estimator, the interested population parameter is mu, then we use the relevant statistic x bar, then using the sample data we calculate the single value. That's why we call 2.6 as a point estimate for the population parameter mu. The 2.6 is the estimate of mean mu. Then see the properties of point estimate, good point estimate. Properties of point estimation. There are several properties, actually 4 properties, but here we concern about the first 2, unbiasedness and efficiency. There are another 2, sufficiency and consistency, but most important 2 properties are indicated in red colors, unbiasedness and efficiency. Then see how to define the unbiasedness. An estimator is unbiased if the mean or expected value of its sampling distribution equals the parameter estimating. That means this is the estimator theta hat. Now we are going to make a decision about, now for example, suppose population parameter is theta. Now we use theta hat as an estimator to make an estimate for this population parameter theta. Here says that this theta hat is an unbiased estimator, and estimator is unbiased. The expected or mean value of this estimator should be equal to the sum is equal to parameter estimated. That means expected value of theta hat should be equal to the population parameter theta. If this is satisfied, then we can say that this theta hat, this estimator, is an unbiased estimator. Efficiency. The concept of efficiency refers to the sampling variability of an estimator. Now suppose we have two unbiased estimators to estimate the same, if two competing estimators are both unbiased, there are two unbiased estimators for the population parameter. If one with the smaller variance, for a given sample, same sample size, is said to be relative more efficient. Now suppose there are two estimators to estimate the particular parameter theta. Suppose theta 1 hat and theta 2 hat are both unbiased estimators for estimating this theta, are unbiased estimators for the population parameter theta. Then calculate the variability of these two. The less variability belongs to, indicate the less variability belongs to the first estimator theta 1 hat. That means standard deviation of theta 1 hat or standard error of theta 1 hat is less compared to the standard error or standard deviation of the second estimator. Therefore we can say the theta 1 hat or the first estimator is more efficient than the theta 2, the second estimator. Therefore theta 1 is relatively efficient than theta 2. The assumption here is that both these two estimators are unbiased, and we take same samples to estimate, take a point estimate these two estimators. Then we calculate the variability of these two. The less variability parameter is more efficient than the other one. Now see some example for the properties. It have a good properties or most efficient unbiased estimators for the given parameters. Here for population parameter mu, we know the most efficient and unbiased estimator is x bar, because we know expected value of x bar is also equal to mu. Therefore it is an unbiased estimator, and also here says that it is more efficient than the other ones. These are the example for the most efficient and unbiased estimators for these three parameters. For mu, the most efficient and unbiased estimator is x bar. For the sigma, the most efficient and unbiased estimator is s square. For the population proportion capital P, most efficient and unbiased estimator is sample proportion simple p. Now we come to the end of this session. Through that session we just discuss about the sampling distributions of sample mean and sample proportion, and also we discuss few applications, and in the later part we just introduce the inferential statistics, and we just discuss about the point estimation, and finally we just discuss about some properties of good point estimators. In the next session we'll discuss about the interval estimation. Thank you.